So my name is Gordon Cooper. I'm the product marketing manager for NXP's Cortex-M4 products. I have with me Bob Boyce from ARM, particularly from Keil. So he's actually going to show you the hardware working and talk through the software development tools. So my job is going to give you the introduction of the 4300. I will give you the introduction and the 30,000-foot view down into why did we pick dual core, how does the communication work, and then I'll hand you off to Bob, who will go into the development tools and how all the debugging works. Okay, here's an ARM slide for you. Most of you said you had knowledge of ARM processors. So there's a fairly solid dividing line here between what I would consider the embedded space in the bottom and the application space in the top. NXP, moving forward, is very focused on the embedded space. So we have a long history with ARM 7 and ARM 9. We do have some Linux support for ARM 9, but you need the memory management unit. So in the embedded space, we're very focused on the Cortex-M moving forward. Cortex-M0, the M3, the M4, the new M0 Plus, et cetera. So a quick explanation for those of you who are not familiar with the Cortex-M family. If you're familiar with the ARM 7, very solid microcontroller. ARM took the ARM 7 and redesigned it and made the Cortex-M3. So think of the M3 as sort of a next generation ARM 7. They added more interrupts. They made it a little bit faster. They made it better power consumption. We sell a lot of ARM 7s, but for new designs, we would encourage people to look at the Cortex-M3. We do have some pin-compatible versions to make the transition easy. So now you have ARM with the Cortex-M3, very solid microcontroller. Then they said, well, let us go after the 8 and 16-bit space. And to do that, we need to cost reduce. We need to make power consumption better. So they came up with the M0. So the M0 is a reduced instruction set of the M3. Slightly less performance, you run it slower, but more power consumption, and you get down to sub 50-cent cost. So you're not going to go after all the 8 and 16-bit, but it's a good start. Then they said, okay, great, what about the DSP space? The M3 can do signal processing, but the single cycle multiply is 3 to 7 clock cycles. Well, that's not very good in a DSP world where you want it to be 1 clock cycle. So they took the M3 and said, let's make an M4. Now, for microcontroller purposes, there's no real performance benefit. But if you're doing signal processing, 3 to 7 clock cycles to 1 clock cycle is a big deal in the inner loop of a filter or FFT. They added a few more things. They added some SIMD, single instruction multiple data, that helps you with optimizing code. And they added an optional floating point unit. Now, the optional floating point unit means that anybody who licenses the M4 can choose to put the floating point unit in. And in almost every case, we put the floating point unit in. 32-bit resolution floating point unit. So those are the fundamental differences. Now, what we'll talk about is the 4300, which took the M4 and said, hey, let's throw an M0 on there as well. So we'll talk about why we did that and how it fits on the bus. Just a quick comment, they're all code compatible. So whatever runs in the M0 will run on the M3. Whatever runs on those will run on the M4. So having a dual core, you can use one set of tools and one set of software, makes it very nice. So it's an asymmetrical dual core, but you don't have to have 2 separate tool chains, 2 separate instruction sets, et cetera. So from an NXP point of view, we have the 1100 and 1200 is our standard standalone M0 families. The 1300 has some pin compatibility with 11. The 1700, a lot of pin compatibility with our older LPC 2000 ARM 7 family. And then these are some of the newest parts. The 4300 is what we'll talk about. This is the dual core. And then there's the 1800, which is almost the identical part, but with a single core M3, a little bit less memory, and missing one of the advanced peripherals. So it gives you a nice platform that says, hey, if you don't need the performance of the M4, you can actually start at the 1800, drop in a pin-compatible 4300 down the road if you need the extra performance. This is the system diagram for the 4300. A lot of peripherals, a lot of I/O. I'm not going to go through that in detail. There's a lot of videos on NXP's website. Or if you go to YouTube and look for LPC zone, where we talk about all these peripherals. We're really going to focus on the dual core here. But just to mention, CAN, USB, Ethernet, LCD, and all your sort of standard serial interfaces are all included. The green boxes are the 2 boxes that are ARM IP. So this green box over here is the M4 core with a memory protection unit, the interrupts, the floating point unit, et cetera. And over here, you have the M0 core. And we'll talk about how they can both coexist and sit on the same bus, and then really, how do you program this part and how do you debug this part, which is really the intention of this talk. Again, I won't go through the details, but how does a company differentiate in the microcontroller space? Anybody with enough money can go off, any company with enough money can go off and license a core from ARM. So if I've licensed an M4 core, and there's starting to be a lot of them out there, how do we differentiate? Well, there's really 4 ways. One is on the core, one is on the memory, one is the peripherals, and the last one I would kind of lump software and support in there. So we as a company continue to look for ways to provide our customers something that solves their problem but also differentiates ourselves from the competition. So on the core, we could have put one M4 down, but we said if you're really serious about signal processing, let us give you the entire M4 to do that, and let's give you the M0, very small from a silicon point of view, to do all your I/O processing and really offload the M4. We have 1 mega flash, very common out there. We also have a flashless version. And the flashless version is lower cost, and you can interface to our SPI flash interface, which I mentioned in a few slides. Dual bank flash is not unique, but not that common, where you have 2 banks of flash. Now, with 2 banks of flash, you can execute from one while you're programming the second bank, or you can give one to the M4 and one to the M0, no contention, and split up your memory partitioning that way. So some choices there. I'll talk about the peripherals a little bit later. We have high-speed USB. We have the high-speed PHY built on chip, which is nice. And I've mentioned the pin compatibility with the 1800. And just to give you a visual look, pin compatible, M3, 1800, 4300, huge overlap in terms of their peripherals and performance. The 1850 runs at 180 megahertz versus 204. Dual core, a little bit more SRAM in the flashless part, and then this new peripheral that I'll mention. But essentially, very similar. So here's 3 questions to ask yourself. Do I really need an M4? One is, do I really need to do signal processing? Will I take advantage, my code take advantage of the single cycle multiply accumulate, or the SIMD instructions? And if the answer is no, okay, then do I want to use the floating point unit, which only is available in the M4? If the answer to that is no, then from an NXP perspective, I would ask you, do you want dual core? And if you're like, not really, then the 1800 is a great part. And it also gives you, as I said, a roadmap to the 4300. However, if you need any of those things, the 4300 is the part for you. I won't go into detail on the part families. The top is our flashless part shipping today. We'll actually be handing you an eval board with the 4330 on it as you walk out. Bob's going to show a board with the 4350. The difference is that has an LCD versus the 4330 is 2 USB, Ethernet, all the other features. The flash parts, we have working parts now. Everything looks great. We're just building up enough parts and we'll release it into distribution in the next 1 or 2 months. So you'll see our flash parts coming out very soon. Okay, so why dual core in the embedded space? So I think of 3 good reasons why the dual core is a benefit to you. And it's not going to be a benefit in all applications. But if you need the performance, there's no question that at 204 megahertz, 2 cores in the embedded space is going to give you the most performance that is out there in the Cortex-M space. Now, performance isn't that important. Maybe an integration path to a smaller footprint is important. You can take 2 MCUs, integrate into a very small package, maybe a 9 by 9 mil package. A low-end DSP and an MCU, another great way to integrate, depending on how much performance you need from the DSP. So that's the second reason for the dual core. And the third one is maybe the least obvious. But if you take, particularly you guys who have done DSP programming, if you're doing real-time programming and you have a certain amount of time to respond before the next interrupt comes in, you really don't want to start worrying about that USB interrupt routine that's pulling time away. If we separate it for you and let the M0, completely separate core, handle all the I/O intensive algorithms and let you have the M4 for signal processing, it drastically makes your programming life easier from a partitioning point of view. Now, as long as you can easily debug that, which is what Bob will talk about, then it should make your programming life easier. So if I drop 2 cores on the bus, and the bus contention means that they're taking turns, there's no benefit. And this is where the bus matrix comes in. So NXP has the bus matrix on all its parts. The top here shows you some of the bus masters. So DMA, Ethernet, USB, SD cards, LCD, all those could be bus masters. So in this case, we just add the M4 and the M0 up here. And over here are slaves that can be accessed via the bus. You see we've broken the SRAM into multiple blocks. We've broken the flash into 2 blocks. So as you partition your code or partition your memory spaces, the best thing to do is take the M4, give it certain blocks of memory, give the M0 other blocks of memory, and the bus matrix will make sure that there is no contention. So as long as you're not accessing the same block of memory, you have no contention. You can run both at full speed. Now, of course, there's going to be cases where the M0 drops something in memory and says to the M4, hey, you got something in memory, go get it. And there's a possibility that they could be trying to get it at the same time. The little triangles here represent bus arbitration. So if that does happen, it's automatically handled by the hardware. You don't lose anything if there's any contention. So you may be familiar with a symmetrical dual core. In a symmetrical dual core, you really take your code and it's partitioned across 2 cores to run faster. So it takes one set of code and runs it both. So this is not a symmetrical dual core. This is an asymmetrical dual core. So in an asymmetrical dual core, you have 2 processors really intended to do two different functions. What those functions are really up to you and how you partition them. But it really is best to think of them as 2 separate microcontrollers in your system. They just happen to be on the same chip. So if you think of it that way and you partition the resources appropriately, you can actually say, all right, I'm going to give you this memory to the M0 and these peripherals, and I'm going to give the M4 this memory and these peripherals. It's the best way to sort of partition it. So you actually design them separately. You design the M4 and the M0 separately, and then you debug them together, and that's what Bob will talk through. On reset, the M4 comes up first. So on reset, the M4 is, if you will, the master. Once that happens, it brings the M0 up, depending on what you do in your boot code. And then from that point on, either one could be in control of the system. So application dependent, but maybe you have a system that says, look, I want to have the M0 run at a slow speed, and then I want to wake up the M4 and run really fast to do math and then go to sleep again. And the M0 is, if you will, sort of the master. There's no official designation, but it controls the system. Or you may say, look, I'm going to have the M4 be in control, and then the M0 is just going to be like a slave I/O processor that just handles the I/O for me. You can treat it either way. But on reset, the M4 is the one that comes up first. OK, how do they communicate? So we have something we call interprocessor communication. It's actually really straightforward in the sense that both cores can interrupt each other. And then you would designate a small section in internal SRAM for, if you will, mailbox registers. So let's say, as an example, the M0 gets some USB code in and works the stack and through DMA dumps it into internal memory. How does it let the M4 know? Well, it would probably go into this memory space, read a location and check for status. And if the M4 needs data, it would then probably write something to the space that says, data's ready. Maybe it sets the first location in memory, maybe the size of the buffer, and then it interrupts the M4. The M4 then goes into the memory space, reads it, and says, oh, I've got data. Now, we've come up with a couple examples for you of this interprocessor communication, but there's no magic in it. You can take those examples and modify them. You can create your own example, but it's pretty straightforward. We have a very simple interrupt-based one. We have one that's more API-based. So we have several examples for you to get started with. So Bob will go into detail on the code, but the key thing I want to mention here is both cores are in the same JTAG scan path. So the same debugger can be used to debug both of the cores. All right, very quickly, I just want to mention from a peripheral point of view, we do have some unique peripherals that are only available at NXP. There's serial GPIO, which effectively is up to 16 lines of I/O with shifter registers and timers. What that allows you to do is combine these to generate just about any single 4-bit, 8-bit, 16-bit interface. So if you wanted to have another I²S or I²C, you can actually use the serial GPIO to emulate another interface. So if you say, geez, if they only had one more UART, or oh, if there's only one more I2C, this will do it for you. It actually also can be high, low, or tri-state. So if you want to do an I2C, you have to be able to tri-state the bus, and it can do that as well. Okay, the state configurable timer is our answer to people saying, hey, can you come up with a unique timer to do some system, whether it be motor control or dead time analysis, whatever it might be. We said, well, why don't we come up with one that's so flexible you can do just about anything you want with it. So we give up to 16 lines, and it's a state machine. So if you think of a PWM, you can have one waveform. If we give you 32 states of a state machine, you could come up with just about any combination of waveforms that you want to. And so the state configurable timer actually has a tool that you draw out your drawing as a state machine, and you can generate just about any waveform that you want to. The last one is probably, hopefully, the easiest to understand. This is our SPI flash interface. So if you're familiar, how many of you are familiar with quad SPI? 8-bit, right? Maybe sometimes 16-bit for the larger memory spaces. You can get up to 256 megabits of external flash in a very small package. It's 4-bit line if you're using the quad SPI, and this is a 32-bit processor. But this SPI interface makes those 4 bits look like internal 32-bit memory. So we basically make it look like virtual internal flash. And we have some accelerators to make it run fast. So even though the initial access might be slow, we essentially have something cache-like that allows you to, if your code is looping, to get pretty fast performance. Better than 50% of the internal speed of the SRAM you can get through this little 4-bit interface, depending on how your code runs. So the cheapest way to start with one of these is the flashless part and a small quad SPI flash. That's going to be cheaper than the 1 meg flash part, for example. And you can add 4, 8, 16 meg of flash. Here you're using the USB, the M0 to handle the USB stack. We've got audio streaming, 2 channels of audio streaming from a PC. Comes in, sticks it in memory. The M4 says, OK, I got it. And 80% of the M4 is used to do signal processing. Now, it goes from 2 channels to 7.1 channels. It adds some virtualization. It adds some other effects to it. And then it dumps it back to the M0, who outputs it via this configured serial GPIO to look like 7.1 audio, basically 4 I2Ss. So there's an example of all of it working together. Now, could you do this on a single core M4? You could, but then the M4 is going to handle the stack and handle this, and probably run a little bit less than 204 megahertz. So yes, you can, but if you want the maximum performance, this is where the dual core is a benefit from a signal processing point of view. Which brings me actually to our list of useful locations. NXP's microcontroller site here, of course, is all the data sheets and corporate information, if you will. Keil has keil.com/NXP. So if you're interested in Keil for NXP, go to that location. Now, LPCware is an NXP sponsored site, if you will. We have our corporate site, nxp.com. We've created LPCware as an engineer-to-engineer community. So that's a place that will upload code, will upload schematics, upload things that engineers can use. So I would strongly encourage you to go look there. When you get one of these boards we'll give you today, continue to check there for more code examples. These boards aren't even for sale yet. I've just got the box a couple days ago, so you guys are getting the first batches. So as we add more information, check back on LPCware for more code examples. Yahoo Groups, we don't sponsor, but we do support. It basically is a great place to ask questions for people who are using NXP microcontrollers. You can go to YouTube, our YouTube channel, LPC Zone, to get a lot of videos. This session is being videotaped. It'll actually be posted on this site. So if you say, what was that guy talking about? You can go check and see the video online in a week or 2. And previous sessions that we've done. And lastly, if you happen to be a Twitter fan, what you'll get is updates on new press releases, new parts, et cetera. OK, just a couple more slides, and I'll turn it over to Bob. From an evaluation point of view, from a flashless parts, this High-Tex board has been around for a little while, keeps selling out. This is the part that's brand new. As you see, April 2012. You guys are getting it today. Hopefully, I got enough. I think so. 4330, 100-pin BGA, a lot of features crammed in a very small package. What Bob is going to talk about today and show is the Keil board. I really like the Keil board. When it becomes available in a month or two, it'll actually have our 1 meg flash part. So if you want to look for that in a month or two, great little board. He's going to use that from debugging. In his case, he's using the flashless version that we populated, but as I said, when we start selling it, it'll be flash.
A couple things I'd like to address, and that's about, he was talking about the CMSIS. So CMSIS is a standard that ARM has been promoting, and it's been accepted by almost everybody now. And the first part of the CMSIS is we're trying to make the header files and manufacturer peripheral files more as a standard. So as you look at these things, you'll start to recognize them, and they're simplified, and mostly, except for one file, they're in C code language. The next part of the CMSIS was the DSP part, and so as he mentioned, ARM is providing DSP functions, libraries, and these are available on the website. And so they're free for not only Keil products, but for IAR and a bunch of others, so there's no restrictions on using these things. And they will work on the Cortex-M4, they work on the Cortex-M3, but obviously not as fast, because they don't have the M3 doesn't have the DSP instructions. And then the next thing is the latest version of the CMSIS is called the CMSIS RTOS. And so we're making a standard so that you can fit different RTOSs onto the processor without an awful lot of porting issues. And we've also reduced, we have an RTOS called RTX that Keil created. And what we're doing is we're giving this with source away free now. And we have ports for Keil IAR and also for GCC. So this, I'll actually show you how this works and so on. Hitex has a very interesting power device that measures power and puts it onto or correlates it to your source code. So they have this demonstrated to show it's a really cool unit, and it uses this Ulink Pro, which is an ETM device. But I would urge you to go down and see them. If you're used to using ARM7 and ARM9 and you're considering switching over to a Cortex-M device, you'll notice quite a bit of difference. It's a lot easier to use. You don't have to do all those assembly languages. You have many more interrupts, so each peripheral can have its own interrupt. And you have a systic timer, so it's a dedicated timer for the RTOS. The M4 has it, and the M0 too, but not in this particular part. But and they also have core site debugging. So we've added a lot of debugging things to the Cortex-M device. And so we have serial wire viewer. I'll show you how that works, and also the full trace, full program trace. And this is included in the Cortex-M4 that's here, and also nearly every, if not all, of the Cortex-M3 devices from NXP have ETM also, and they all have serial wire viewer. So it's a way of getting debugging information out from the core in real time without stealing cycles or any source, any code stubs in your source and stuff like this. So let's start. We'll just fire this up. So what I have here is, you can see here, this the Keil stuff. So here's the startup file. This is the only file that's an assembly, and I suppose you could write it in C, but it's it's pretty easy stuff here. So this is like load the initial stack pointer, set up all the IRQ handlers, right? So for all the peripherals. This is something you never had in ARM7. There's tons of other features in the Cortex-Ms and the heap and the stack and so on and so forth. And then we have the startup file. Sorry. System. And so this sets up the clocks and so on and so forth. So this is all completely written in C, and so you can find that this is a lot easier to work with than the assembly files. So what I have here is I'm hooked up to that Keil board, the 4300 board, with the Ulink 2, and so you could also use a Seger J-Link. We support that one also, the black box. So I can compile a program. It's already compiled. So we're running out of RAM. That's why I didn't program the flash, because we're actually running out of RAM. And so I can start this. It's all connected and running. And you can't see it very well, but there's lights blinking here, and it's a motor controller. We have in here, if I go to the, I have to move this up. And so you can see here the blinky. And so let's just roll down here. I have 4 global variables. The RTX operating system is right in here, and it's pretty easy. So we have this bunch of things, and then there's one task 2 tasks. Each of these is one of the 4 motor controller drivers. And so it's pretty easy to get working. I have I'm just switching those global variables off and on to the thing. So I can take this, and I can, this phase C, for instance, I can drop it down into here, into the watch window. I could take the phase D. Oh, that won't work. Let's go back up here. Pick up one here. I can right-click it, or I can put it in this way, add phase here to watch window. And so there's phase B, watch window. So what we have here is we now have, you can see them are updating in real time. This is part of the CoreSight feature that's in the NXP chip. No cycles are being stolen to produce this. And you can also punch values into this without using up any cycles. So if you want to change a value, you just type it in there, and it'll be changed. The other thing we can do here is we'll look at quickly OS support. So now you can see here all oops, where'd it go? We lose a little bit of screen space here. So here you can see that the tasks of the phases, everything is being updated. And this uses the same situation as the watch does. And so we call it DAP, read and write. And so this is, once again, updated. The other part that we have, the event viewer. And this isn't working because we don't have the serial wire viewer turned on, but we'll turn that on right now. So I'm going to stop the program and go in here and V-link to ME. Now, select the trace. We'll enable the trace. And you can see we have things like periodic PC sampling. We can see the data reads and writes. We can see all the exceptions as they're happening. And this all happens in real time. And there's an ITM stimulus, which is actually it's a type of printf statement that uses very few cycles to do that. But everything else does not use any cycles. So now if I go back into the debug mode, run the program, and now you can see that in this display here, that in a graphical format that where you can see where the tasks are coming on and off and stuff like this. So it gives you a really good indication here. And so Reinhard Keil's here, and he told me that we're going to be adding some things to these windows. And this uses the serial wire viewer. So the serial wire viewer is a 1-pin trace output on the chip. So the other thing that we can do is in this window here, and remember I'm doing all this stuff when the program's still running. I haven't stopped the program to enter any of these values. And so if I go down to my window here to my variables, oops. Okay. Where did they go? There they are, okay. So I'm going to block this one, phase A, stick it up there. I'll do phase B, stick it up. Oh, I'll do it this way. Add phase B to the logic analyzer. I'll add phase C and D to the logic analyzer. So now I have these 4 in here, and I have to change the, obviously, the scale. I'll just use 3. You can already probably in the background start to see that things are changing. And so I can zoom this out. And there's our 4 waveforms. So in the Cortex-M4 and M3, you have 4 of these because there's 4 comparators in the chip hardware. Another interesting thing that the Cortex-M has, if I just go down to one of these tasks, and if I just set a breakpoint there, you can set breakpoints on the fly with the Cortex series. You don't have to stop the processor. And I believe that this device has 8 hardware breakpoints. Let me run this. I have to show one more thing here, and that's the trace records. So here's this ITM, so that's the information that's coming out of the RTOS. So normally we can filter that out. Now we have the exception. So here's one of the places where all the exceptions show up. So exception entry is when an exception goes in. Exit is when it goes out, and return when all the tail chaining is over. So when that's when all the interrupts have gone out, and then it's back into your main program. If I take this out, the exceptions, then there's the data write. So this means that data of 0 was written to this address, and I could have turned on the PC. They'll tell you which instruction wrote that address. Okay. And this data, this information is all collected in real time. I have to stress that. There's no cycles stolen to do this. So let's leave this one, and we'll go into a dual core now. So I use just a single core now to keep things nice and simple. But what I'm going to do is I'm going to hook up the U-Link Pro, and so it adds ETM. Okay, so this is our, I'll leave it open here for a while. So have to program the flash. So that's done. So it's the external flash. And then I enter the debug mode, and I'll run it. So what's happened here, you can't see it. Well, there's like 4 lights blinking here. So what's happened is both the Cortex-M4 and the Cortex-M0 are already running. Because remember, they said that the Cortex-M4 starts up first, and it starts, it loads the program for the Cortex-M0, and so both cores are running. But we can control both cores here. Now the code that's created is this. This is what the program from the Cortex-M0, this is what is sent to the Cortex-M4, and this is what's run in there. So I can, I'll stop this for a second. And I'll show you. So in this, so here's the U-Link Cortex Pro debugger, and in the settings we have, here's how we communicate with both cores. So there's the first, it's a JTAG chain, and there's the first one. This is the Cortex-M4, and this is the Cortex-M0. So I've selected the Cortex-M4, so I just hit OK, and I'll just minimize this a bit. And I'm going to start up a second instance of the MicroVision. And this one already is selected for the Cortex-M0. So this is where you would write the program for the Cortex-M0, compile it. It creates that other file that I showed you that the Cortex-M4 picks up and programs into the memory, and away it goes. And that's basically roughly how you do this. So what I can do here now is I have 2 instances of the MicroVision running, one for the M0, one for the M4. We compiled the program before. That's easy. So I'm going to enter debug mode, and so I can, that's the M4. So the M4 is, now right now both the M4 and the M0 are running. Under normal circumstance, you can run these on 2 screens, right? So this would be a little easier to do. So I've entered debug mode on the M0, and there's the source code, and I can run it, and now they're both running. And now I can turn the M0 off at my will, or I can turn the M4 off at will. So now I'm controlling them independently of the M4. So the lights all are blinking in a different sequence here because I'm turning things off. So the M4 is on, M0 is on, the M0 is off now, so this kind of stuff. This is how you can debug these, set breakpoints. The other thing we can do is, I think, I have this. So I can go up here, see if I can find a, whoops, link key. So this led on, this is a little global variable, so I can add it to the logic analyzer, and I can, this one here, I can add it. Let's add it to something a little more realistic. Whoops. Let's see. There we go. Okay, so what we have here is this is the serial wire viewer now is the code that's turning off the on and off the LEDs. So now I'm picking it up and displaying it here. And so you might say, if it's supposed to be 1 or 0, what is this? That's an interesting thing. I haven't found that answer out yet. So I have to ask Martin what he did to create that thing. So that might be an anomaly. I'm not sure what it is. Or it might be somewhere in the code he's set this. It actually goes up to FF. That's what happens here. So these other ones are 0 and 1. You can also, if I move this over a bit, this is there, do this like this. There we go. So you can all do this, get all kinds of timings off of this and different things with this cursor. Set a thing and then figure out what different times is. So it's quite interesting here. So, okay. More thing that comes out of the Cortex-M4, this guy here. And we're only going to do this on the Cortex-M4 for simplicity. And I can program the flash. So remember I said this has the ETM, so what do you get out of the ETM? You get all the program counters, and once we know all the program counters, then we can really find out an awful lot more information. And so one thing here is we have this is just another use of the logic counter. So this is just an A to D controller, just a little pot on here, so that shows up. If you look in here, you can see, code coverage. So these green means these instructions were executed. And somewhere in here, there will be some that aren't. I don't know where they are. They're grayed out. And then also it indicates if the branch was taken or if a branch was not taken with different colors. Here you have timings, how many times this was called. And you can see this is being updated in real time. How many times it was called or how much time was spent in those functions. Out of the ETM, you also get, performance analyzers. And so here you can see it gives you indication, and you can also, we'll soon be able to save this stuff. And so you can also see here where your program is spending its time. And this is, as you can see, is being updated in real time because we're collecting ETM as the program's running. If we go to the trace data, you can also see this is at the startup. And so you can see here, this is all the code, the assembly language instructions, when they happen, and then some source information in here. And if there's some source code that was associated with this, it'll show up in this window too. You can you click on here, and it'll take you to that spot in the source code. Okay, so that's the end of my stuff.